Welcome to G Fun Facts Online. Today, we are turning away from the dusty museum halls filled with silent skeletons and looking down at the ground beneath our feet. We are exploring Ichnology, the science of decoding behavior from prehistoric footprints. When we look at a Tyrannosaurus rex skeleton, we see a monster frozen in death. But death is only a single moment. What about the millions of moments that came before it? To find the living, breathing animal, the creature that ran, hunted, cared for its young, and struggled through the mud, we have to look for the shadows they cast in the stone. Unlike bones, which preserve the organism, trace fossils preserve the activity of the organism. They are biomechanical data points and narrative clues, locked in rock for millions of years. Let's start with the science of how these shadows survive deep time. The existence of a fossil footprint is actually a statistical miracle. For a bone to fossilize, an animal just needs to die and get buried. But for a footprint to fossilize, the conditions must be exactly right while the animal is still alive and moving. It's what geologists call the Goldilocks consistency. If the ground is too wet, the walls of the print collapse into a shapeless blob. If it is too dry, the foot makes no impression at all. The mud needs to be firm enough to hold detail, yet plastic enough to mold under pressure. Once that perfect impression is made, it has to be buried rapidly and gently, perhaps by a river flood of soft silt or a layer of wind-blown sand, to protect it from the elements until it turns to stone. When we find these prints, we aren't just looking at pretty shapes, we are looking at hard mathematics. This brings us to the physics of movement. How do you look at a hole in the rock and know exactly how fast a dinosaur was running? It seems like magic, but it is pure biomechanics. In 1976, British zoologist R. McNeill Alexander revolutionized this field. He realized that animals of similar shapes move in dynamically similar ways. By measuring the stride length, that is, the distance between two successive placements of the same foot, and combining it with the animal's hip height, which is usually 4 times the length of the footprint, we can calculate speed. Using Alexander's formula, we can determine if a dinosaur was strolling, trotting, or running for its life. This math shattered the old Victorian image of dinosaurs as sluggish, tail-dragging lizards. We now know that large theropods could move with terrifying grace. We can even read the nuances of their movement through what we call displacement rims. If the mud is pushed heavily to the outside of the track, the animal was turning. If the toe impressions are deep and the heel is missing, it was sprinting on its toes. We can literally see the acceleration. Perhaps the most gripping stories come from our own history. Let's talk about the human story found in the mud. Nothing resonates quite like the footprint of our ancestors, because they look so startlingly familiar. In 1976, in Laetoli, Tanzania, Mary Leakey's team found tracks of Australopithecus afarensis dating back 3.66 million years. These prints settled a massive scientific debate. They proved that our ancestors walked upright on 2 legs millions of years before they developed large brains or stone tools. The tracks show deep heel strikes and distinct arches, just like ours. For a long time, this trackway was romanticized as the first family, a male, a female, and a child. However, modern analysis suggests a different social structure. The huge size difference between the adults suggests high sexual dimorphism, which in primates usually correlates with a harem structure, one dominant male and multiple females, rather than a nuclear family. Moving closer to the present, we have the explosive discoveries at White Sands National Park in New Mexico, occurring between 2018 and 2025. These are called the ghost tracks because they are invisible when the ground is dry, only appearing as dark spots when the earth is wet. These tracks have completely rewritten the timeline of human arrival in North America. Seeds found embedded in the footprints were dated to between 21,000 and 23,000 years ago, placing humans on the continent during the last glacial maximum thousands of years earlier than we previously thought. But White Sands offers more than just dates. It offers drama. One specific trackway records a life and death interaction. We see the tracks of a giant ground sloth walking across the mud. Then, human footprints appear inside the sloth's tracks. The humans were stalking it. Suddenly, the sloth tracks change. The animal rears up on its hind legs and spins, creating what researchers call flailing circles. It was reacting to a threat. Simultaneously, human tracks approach from a different angle on tiptoe. This is a snapshot of Pleistocene strategy, humans coordinating to distract and flank a 2,000-pound monster. Another trackway at White Sands tells a softer story. A woman or adolescent walked for nearly a mile in a straight line. Occasionally, a tiny set of toddler prints appears next to them, then disappears. She was carrying a child, shifting the baby from hip to hip, and occasionally putting the child down to rest her arms. The depth of her prints proves she was carrying extra weight one way. On her journey, a mammoth and a sloth crossed her path, and she didn't even deviate. To her, these giants were just part of the scenery. Now, let's jump back to the age of dinosaurs. The most famous site is arguably Glen Rose, Texas. For decades, there was a controversy here regarding so-called man tracks found alongside dinosaurs. Ichnologists have thoroughly debunked this. The human-like prints were actually dinosaurs walking on their heels due to deep mud, and when properly cleaned, the claw marks are visible. But recent droughts in Texas have revealed new secrets. In the Paluxy riverbed, we see a massive trackway of sauropods, long-necked dinosaurs, being followed by a large predatory theropod. The predator steps a line suspiciously with the prey's path. While we can't prove they were there at the exact same second, the alignment suggests a hunt, or at least a predator using the herd's path as a convenient highway. Speaking of highways, in 2024 and 25, excavations in Oxfordshire, England, uncovered Europe's longest sauropod trackway. Spanning over 200 meters, these Cetiosaurus tracks allow us to see changes in gait over long distances, which is incredibly rare. We also have evidence of complex behaviors from Bolivia's Carreras Pampa site, where over 16,000 footprints reveal a chaotic dance floor. Crucially, some tracks show only the tips of claws scraping the bottom, with no heel impression. This proves that theropod dinosaurs were swimming, buoyant in deep water, paddling to cross rivers or lakes. Footprints also prove herding behavior. We find parallel trackways of dozens of animals moving at the same speed. In some sauropod herds, we see a nursery structure. The small footprints of juveniles are exclusively in the center of the trackway, flanked by the massive prints of adults on the outside. This is direct evidence of protective herding, protecting the young from predators, just like modern elephants. Ichnology goes even deeper than dinosaurs. In Ireland, on Valentia Island, we find tracks from 385 million years ago. These are the lumbering steps of a tetrapod dragging itself out of the water, the literal evolutionary moment of life moving from ocean to land. In Scotland, from the Carboniferous period, we find the tracks of Arthropleura, a millipede-like creature that was 8 feet long. The tracks are two parallel rows of many legs, and they are remarkably straight. This tells us that this giant bug had no predators. It was the tank of its ecosystem, bulldozing through the undergrowth without fear. We can even study the most intimate of trace fossils, coprolites, or fossilized feces. A famous T-Rex coprolite contained pulverized bone fragments, proving that the tyrannosaur was a bone eater with jaw pressure strong enough to crush skeletons. In early human coprolites, we find parasite eggs, helping us map the history of disease. So what is the future of this field? It is digital. We are currently in the golden age of ichnology. We no longer rely on heavy plaster casts. We use photogrammetry and drones to create sub-millimeter 3D models. We can apply false color heat maps to these digital models, making a weathered track pop with detail, revealing skin texture or the slip of a heel that the naked eye would miss. Artificial intelligence is now being trained to scan thousands of square meters of drone footage to identify footprints that humans might overlook. Ichnology is the closest we can get to time travel. When we place our hand over the three-toed print of a dinosaur or stand next to the ghost tracks of a human mother carrying her child, we are connecting with a living intent. We see the hesitation, the speed, the struggle. The ground beneath us is a manuscript written over and over again by the creatures that came before. We just have to learn how to read the story. Thanks for listening to Fun Facts Online.